what is the delta V budget for launch vehicles? Well, the delta V budget is a summing up of the losses that have to be overcome by the launch vehicle in order to get into orbit. We have to get to a desired velocity, and the propulsion system must achieve that velocity plus make up for losses from drag and what's called gravity loss. But there's also a third loss called the steering loss. Let me try to explain what that means. So here's our rocket. And the rocket is launched at first straight up to clear the tower and to get high in the atmosphere. And it starts to pitch over in order to start accruing velocity along the downrange direction so that it can finally achieve orbit. But in the optimal steering law, it turns out that the rocket will actually pitch downward near the end, which is not along the current velocity vector, and that results in some losses that have to be made up by the propulsion system. Let me explain this in more detail on the blackboard. So what do we mean by delta V steering loss? Well, let's consider the optimal trajectory that takes a spacecraft into orbit. So let me draw my axes, where this is the downrange distance, and this is the altitude. And we have a desired altitude and velocity. So let's say this is the altitude we want. And we'll draw in a vector here representing the desired velocity. When we launch the rocket on an optimal trajectory, it will follow the following path that takes it all the way up to the altitude and velocity we need. So now to consider what we mean by steering losses, imagine the rocket launching at first directly vertically, and then it starts to pitch over and follows the optimal trajectory that gives us the minimum propellant to get into orbit. Well, it turns out that the rocket has to tilt or pitch over, and sometimes is even pointed towards the ground near the very end in order to cancel out the vertical momentum we picked up during the launch. And if we consider at any point along the optimal path that these represent the velocities, we see that because of the optimal steering law, the rocket is not necessarily pointed or aligned with the current velocity vector all the time. And so this misalignment between the thrust and the velocity vector accounts for certain so-called cosine losses. And so the thrust is not delivered entirely to add to the velocity, and that is where we get the velocity steering losses. By the way, in the case of launching the LEM, the lunar module, from the surface of the moon into orbit, the angle at the very end for the thrust vector was a negative 4 degrees. The steering loss, delta V steering loss, for the Saturn V was 243 meters per second. So our propellant has to make up for that loss. This is a very difficult calculation to do, and so one practical way of approaching it is to look up the steering losses on similar launch vehicles to the one that we're trying to design.